It helps to predict the direction of the reaction at any stage by using the reaction quotient. The equilibrium shifts in order to minimize the change and new equilibrium is established. When you remove the products, what will happen? Then reactants concentration also increases. First of all, catalysts. What is the role of catalyst in chemical reaction? It increases the rate of the reaction. Hello everyone, I am Venu Prasad, Department of Chemistry, Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. Today I am going to do equilibrium session 2. Okay, now let us study today the expression of gaseous reversible homogeneous reaction, relationship between Kp and Kc, applications of equilibrium constant, relation between equilibrium constant, reaction coefficient as well as Gibbs energy, Le-Chatelier principle, ionic equilibria, Arrhenius theory, Laurie-Bronsted theory, and ionization of acids and bases, and dissociation constant of weak acids. Now let us study the expression for gaseous reversible homogeneous reaction. Okay. Now let us consider one reaction AA plus B give rise to CC plus D. Okay. Here it is a reversible reaction. Okay. Now let us take reversible reaction AB plus A plus B give rise to C plus D. Okay. And here it is conducted in a closed vessel. This reaction is conducted in a closed vessel at constant temperature. Let PA, PB and PC and PD, okay, be the partial pressure of reactants and products. Partial pressure of reactants and products. Let V1 and V2 be the velocity of forward reaction and backward reaction. It's a velocity of forward reaction as well as backward reaction. Now let us apply the law of mass action for the above reaction. Okay. So if we are applying, V1 is directly proportional to PA into PB, partial pressure of reactants, both. Okay. So if we remove the proportional, then we will get one constant that is known as K1. So V1 is equal to K1 into PA into PB. So K1 is the velocity constant of forward reaction. Velocity constant for forward reaction. Now let us apply law of mass action for the product. So Vz is directly proportional to Pc into Pd. Okay. So if we remove the proportionality constant, Vz is equal to Kz into Pc into Pd. Okay. Next thing is, here what we have to do, here what do you mean by K2? For reactants, we have taken K1 as a velocity constant. Here also it will be a velocity constant for backward reaction. Now let us take at equilibrium. At equilibrium what we can say, V1 is equal to V2. What is the value of V1? K1 into PA into PB, and V2 K2 into PC into PD. Okay. Now let us take Kp is equal to K1 by K2. K1 by K2. Okay. So PC into PD divided by PA into PB. Here we can say that K1 by K2 also we can be written as products divided by reactants. Concentration of products divided by concentration of reactants. Applying mass of law of mass action. So we can write like this. Okay. Next thing is, it is the ratio. Now let us see the definition. Equilibrium's constant definition is, it is a ratio of products of partial pressure of products to the product of partial pressure of reactants. Partial pressure of reactants raised to the power of respective number of moles. Here PD upper side we have given, right? So that is known as moles. Okay. So here P is the pressure and C is the products. Okay. But upper side C we have written, right? That is known as moles, number of moles. Okay. Next thing is relationship between Kp and Kc. Okay. How we can say that Kp is equal to Kc into RT delta Ng. Okay. Then where delta Ng is the, what can we say that delta Ng? Delta Ng is the number of moles of gaseous products minus number of moles of gaseous reactants. So if we are calculating here for ammonia now, what can we calculate? delta Ng is equal to what we can calculate? Number of moles of gaseous products minus number of moles of gaseous reactants. So how much products we have got? 2. 2 minus reactants. How much reactants we have? 3 plus 1. So it is 4. 2 minus 4 is minus 2. So if we are calculating the relationship for ammonia, Kp is equal to Kc into RT to the power of minus 2. Otherwise, we can say like this, Kc divided by RT square. This is the relation for ammonia. Okay. Now let us calculate for phosphorus pentachloride. Phosphorus pentachloride. In reactants, delta Ng. Delta Ng. How much for along products? It is 2. 2 minus. For reactants, how much they have given? Only 1. So it is 1. So how we can write? Kp is equal to Kc into RT to the power of minus 1, not only plus 1, because I didn't get any minus sign here. Okay. So this is the relationship for phosphorus pentachloride. Now calculate for hydrogen iodide. If we are calculating for hydrogen iodide, delta Ng is equal to products. How much products we have got? 2 minus reactants. How much we have got? 2. So it will be 0. So Kp is equal to Kc into RT to the power of 0. So RT to the power of 0 means what we will get? We will get 0, right? So Kp will be Kc into 0. So then it will be always 0. This is the relationship between hydrogen pentaiodide. Okay. Next thing is applications of equilibrium constant. It is used to predict the extent of the reaction, and it is used to direct the how the reaction takes place. So it predicts the direction of the reaction, and it is used to calculate the equilibrium concentrations. Okay, now let us see what do you mean by extent of the reaction. How we will predict, right? Correct, right? So if you are doing a chemical reactions today, you should know that at what time it proceeds and what time it you will get an intermediate, or at how much concentration we have to proceed the reaction. These are all we have to note down when we are doing a reactions. Okay, now let us see how we will predict the extent of the reaction. Just equilibrium constant is directly proportional to, the concentration of products. It's a concentration of products, and inversely proportional to the concentration of the reactants. It is inversely proportional to the concentration of the reactants. It shows that higher the value of K, faster is the reaction. Higher the value of K, faster is the reaction. But it is nearly to the completion. But what we have to think, smaller the value of K, slower is the reaction. And the reaction proceeds rarely. Okay. Now let us see here. If you have got 10 to the power of 3, see here, both the reactants are present in equilibrium. Reactants and products are present in equilibrium. If you get the value of K, 10 to the power of 3 to 10 to the power of 1, all will be in the equilibrium. But if it is less than 10 to the power of 3, here it is negligible. It is very difficult to predict the reaction rate. Okay. Next thing, if your value of K is large, what we can say? Reaction proceeds almost completely. We should think that if your value of K less than 10 to the power of 3, then it is very difficult to predict the reaction. Next, 10 to the power of 3 to 10 to the power of 1, all the reactants as well as the products will be in the equilibrium. But more than 10 to the power of 1, what we have to think? Here 10 to the power of 1's upper side, what we have to think? Reaction progresses very easily. Okay. Next thing is predict the direction of the reaction. We should know, right, whether it is reversible or irreversible, or what we are getting. We should know, right? So we need to think about the direction of the reaction. It helps to predict the direction of the reaction at any stage by using the reaction quotient. By using a reaction quotient. So reaction quotient is the ratio of the products of concentration. Ratio of the products of the concentration to the products of reactants. So we have to think that it's a ratio of products of the concentration of the products then to the reactants. It will quotient means it will find the concentration of products as well as the concentration of reactants. Okay. Next, it is same as equilibrium constant except the concentrations are not necessary for the equilibrium value. If for equilibrium value it is not necessary. Okay. So if quotient value is greater than equilibrium constant, what we can say then? Reaction proceeds to the left, means reactant side. Reaction proceeds to the left, reactant side. If quotient value is less than equilibrium constant, what we can say? Reaction will proceed to the right, that along product side. Okay. Next, if equilibrium constant is equal to the quotient, what we can say? Reaction mixture is in equilibrium, so there is no reaction takes place. If value of quotient is equal to the equilibrium constant, then we have to say that reaction is at equilibrium. There is no change in the concentration of reactants as well as the products. Okay. Next thing is, write the relationship between equilibrium constant, reaction quotient and Gibbs energy, they will ask. Okay. So we have got three terms here, which and all? Delta G naught and Kp. So from three terms we can derive a relationship between three terms. What we can say? Delta G is equal to delta G naught plus RT ln Ke. Okay. So when delta G is equal to 0, at equilibrium delta G will be always equal to 0. Then what we can say? Ke will be equal to Qc. Okay. Next, if delta G greater than 0, delta G greater than 0 and Ke is greater than 1, then what we can say? Reaction is spontaneous. Reaction is spontaneous. So reaction proceeds towards forward reaction. Forward reaction. Then if delta G greater than 0, Ke less than 1, Ke less than 1, then reaction is non-spontaneous. So reaction proceeds in forward direction and it is very minute quantity, you will get the product. Okay. If delta G greater than 0, Ke less than 1, you will get a very less product. Okay. Next thing is Le-Chatelier principle. What we can say that it is a Le-Chatelier principle means just when external stress is applied on a system. It is applied on a system at dynamic equilibrium. Dynamic equilibrium, system shifts the position of equilibrium. It will shift the position of equilibrium so that it is nullify the effect of stress. Nullify the effect of stress means, for example, if you have taken today ice. If you have taken ice and kept in an open environment, what will happen? It will convert to the water at particular time. Means around in 5 minutes it will be diluted or it will be dissolved. But if you keep ice in an open environment and that ice is kept on the vessel which contains another ice cubes, then what will happen? Then also ice will be melted, but it takes longer time to melt because surrounding is also containing little amount of lesser temperature, not in a room temperature. If you are conducting experiments means in open atmosphere, then what will happen? We should note down the temperature of the atmosphere temperature. But if you are conducting the experiments in the presence of ice, what will happen? Then temperature will be decreasing, right? Because ice is surrounding the reaction mixture. So then also ice gets melted, but it takes time. So we can say that equilibrium will be shifted. Correct, right? So external stress is applied on the system. When it is applied, what will happen? Dynamic equilibrium is shifted. Position of the equilibrium will be shifting. Correct, right? So what will happen? So as to nullify the effect of the stress. Okay. So another way of explaining means if the system is at equilibrium, if system is at equilibrium and it experiences a change in concentration, it will experience a change in concentration, temperature or total pressure, the equilibrium shifts in order to minimize the change and new equilibrium is established. Minimize the change and new equilibrium is established. Okay. Next thing is effect of concentration change. What will happen when the reactants are added to the system? Now reactants are added to the system at equilibrium. What will happen? the system tends to decrease the concentration of the reactant. The system tends to decrease the concentration of the reactant, convert into the product. So what will happen? Forward reaction is favorable and equilibrium shift towards the right. First thing we have to think is reactants are added to the system at equilibrium. What will happen? The system tends to decrease the concentration. When system tends to decrease the concentration, reactants are converted into products. So it is a forward reactions. Okay. Next, when products are removed from the system. Now let us take products are removed from the system when it is at equilibrium. What will happen? System tends to increase the concentration of the products by converting reactants into products. So forward reaction is favorable and equilibrium shift towards the right. What will happen? Now you will progress the reaction. It will be at equilibrium. After some time you will remove the reactants. You will remove the system. Here, when the products are removed from the system, they have said. So we should know that one reaction has been progressed. It is you have got the product and you have kept that in the equilibrium. Now you are removing the products. When you remove the products, what will happen? Then reactants concentration also increases. Reactants concentration increases here. Okay. So what will happen when reactants concentration increases? Then forward reaction is favorable. Okay. Next, effect of concentration change. Effect of concentration change means when the temperature of the system is increased. When the temperature of the system is increased at equilibrium, system tends to decrease the temperature. System tends to decrease the temperature by absorption of heat. Then it is known as endothermic reaction. Endothermic reaction. If temperature of the system is decreased, now temperature of the system is decreasing at equilibrium, the system tends to increase the temperature. System tends to increase the temperature. Then what will happen? Heat will be liberated. Then exothermic reaction is favored. Okay. Next, effect of temperature on the equilibrium. Now let us take one example here. Can be demonstrated by taking nitrogen dioxide as a gas. Okay. And it is in brown in color. It will be always brown in color, which demirizes N2O4 gas, and it will be colorless. When it is exposed to the environment, it will be colorless gas. So that is N2O4. So how much liberation takes place? Heat will be liberated, right? So delta H is equal to minus 57.2 kilojoules per mole. Okay. Next thing is effect of change in pressure. Now let us see the pressure. Now we learned concentration, temperature and all we learned. Now let us see the pressure. Okay. If the pressure of the system is increased, now let us increase the pressure of the system. Then at equilibrium, it is at equilibrium. Okay. Then system tends to decrease the pressure. Now system tends to decrease the pressure by decreasing number of moles. So equilibrium shift towards the such side. Equilibrium will be shifted. Okay. If the pressure of the system is decreased, now let us pressure of the system you can decrease. Then when you can decrease? Only when it is in equilibrium. Then system tends to increase the pressure by increasing the number of moles. Okay. Then what will happen? Equilibrium shift towards the such side. Such side also we can say. But when you increase the pressure, we can see some amount of products will be missing, or concentration of products will be very less when you increase the pressure. One time if you increase the pressure, 100% there will be chances of getting a char of the products. Products gets charred. Okay. So we have to maintain a particular pressure when we are doing a reactions. Okay. Now let us take one example. Carbon monoxide gas is treated with 3 moles of hydrogen. You will get methane and water molecule, which is in the gaseous form. Okay. When the pressure is increased here, now let us increase the pressure. Volume decreases. Volume gets decreases, and it favors the reaction in which decreases the number of moles. It decreases the number of moles. In above reaction, forward reaction involves decrease in number of moles. Forward reaction involves decrease in number of moles, and hence there is increase in pressure favors you are increasing the pressures, and it will be favor in the forward reaction. There will be favor in the forward reaction. Hence equilibrium will be shifted towards the right. Okay. Here there is decrease in moles and forward reaction takes place, and what will happen? Equilibrium shift towards the right hand side. Okay. Next thing is Le Chatelier principles on effect of catalyst. Now let us see the catalyst. First of all, catalysts, what is the role of catalyst in chemical reaction? It increases the rate of the reaction. To increase the rate of the reaction, we use the catalyst. But here, what we have to say that catalyst has no effect on the position of the equilibrium. When the reaction is at equilibrium, there is no role of catalyst because it alters both forward and backward reactions. It alters forward or backward reactions very quickly. When the system is at equilibrium, there is no role of catalyst because it alters. What is the role of catalyst? It alters the rate of the reaction. So, if you put a catalyst when the system is at equilibrium, there is no use at all. But if the system is not at equilibrium, if you put a catalyst, it will change the rate of the reactions. Okay. Next thing is ionic equilibria. In ionic equilibria, there are two types of electrolytes. That is, first thing is, one is non-electrolyte and another is electrolyte. Now let us see what do you mean by electrolytes. These are the substances which conducts electricity, both in molten state and in a solution state, both in a molten state as well as in a solution state. Now let us see example is sodium chloride, sulfuric acid and acetic acid. These are the examples for the electrolytes. Now let us see what do you mean by non-electrolyte. Non-electrolyte means these are the substances which do not conduct electricity. They will not conduct electricity at all when both it is in the solid state as well as in the solution state. Example is C6H6 as well as the ethanol. Okay, benzene as well as the ethanol is an example for non-electrolyte. Okay, next thing is electrolytes is of two types. Again, it is of two types. Which and all? Strong electrolyte and another one is weak electrolyte. What do you mean by strong electrolyte? These are the electrolytes which undergoes complete ionization. It undergoes complete ionization. Example is sodium chloride. If it ionizes, you will get sodium plus and Cl minus. And weak electrolyte, these are the electrolytes which undergoes partial ionization. It undergoes partial ionization. Example is acetic acid, ammonium hydroxide. If you take an ammonium hydroxide, NH4 plus OH minus you will get. Okay. Now let us see what is the definition of ionic equilibria. A solution of weak electrolyte, and it acquires a equilibrium. We have to take one weak electrolyte and it should be in a equilibrium state. Then equilibrium state is established between the ions and the undissociated molecules. Then it is known as ionic equilibria. We have to take a solution of weak electrolyte and it should attain equilibrium. After you attain equilibrium, there should be we have to take a ratio of dissociated ion and undissociated ion. Then only we can say that these are ionic equilibria. Okay, because we have to take one molecule, we have to progress one reaction. When you progress a reaction, one of the reactant loses one electron. In your reactions, we have to think that first thing is how much electrons has been lost by one reactant when it attains the equilibrium. So we have to think that we have to take a ratio of dissociated ions divided by undissociated ions. That is the formula to calculate the ionic equilibrium. Okay. Next thing is Arrhenius theory of acids and bases. So according to this theory, acids are the substance which donates a proton, Example is hydrogen chloride. Next thing is basicity of acid. Basicity of acid means it is equal to number of replaceable hydrogen atom. It is equal to number of replaceable hydrogen atom present in one molecule of an acid. Example is HCl, HNO3 are the monobasic, but H2SO4, oxalic acid are dibasic because there are two hydrogens here. So that is known as dibasic. But H3PO4, hypophosphoric acid, that is known as tribasic because of three hydrogens. Okay. What are the bases? Bases are the substance which can donate hydroxyl ion. They should have OH minus ion. So sodium hydroxide is an example for the base, or potassium hydroxide. Okay. Next thing is acidity of the base. If you are going for the acidity of the base, it is equal to the number of replaceable hydroxyl groups. Acidity means just we can say H plus ion, but we have said acidity of base they have said. So base means we should have OH minus ion. So I have taken replaceable hydroxyl groups. present in one molecule of the base. So example is sodium hydroxide. Here one molecule of the base. So one hydroxyl groups are present. Okay, that is known as acidity of the base. Next thing is Laurie-Bronsted theory. Laurie-Bronsted theory of acids and bases. If we are doing this means, according to this theory, acid is a substance. Acid is a substance which has got a tendency to donate a proton. It has got a tendency to donate a proton. Base is a substance which has a tendency to accept a proton, Example is HCl reacts with water molecule. It forms hydronium ion and Cl minus ion. Okay, so these are the example. Here HCl donates a proton. So it is an acid. H2O, it accepts a proton. So it is known as base. Now let us see conjugate acids and base pairs. What do you mean by conjugate acids and base pairs? These are the pairs of acids and bases which differ by proton, These are the pairs of acids and bases which differs by proton. Okay. Next thing is conjugate acids and bases. What do you mean by conjugate acids and bases? These are the pairs of acids and bases which differ by a proton. Here you see ammonia. It is reacted with water molecule. You get ammonium ion, conjugate acid. One of the hydrogen, it increases the H plus ion. Correct, right? So that is known as conjugate acids and base pair. But here, if you have taken water molecule, when it comes here, it has got only OH minus ion. It has lost one proton, one H plus ion it has lost. Okay, so that is known as conjugate acids and base pair. Okay, next thing is amphoteric substance. What do you mean by amphoteric substances? These are the substances which act as both acids and bases. Then it is considered as amphoteric substances. Example is H2O and ammonia. Okay, next thing is Levy's theory of acids and bases. Levy's theory of acids and bases means, according to this theory, acids are the substance which accepts a pair of electron, but base are the substances which donates a pair of electron, So here you see boron trifluoride reacts with ammonia. You will get a lone pair of electrons from ammonia to the boron trifluoride. So I have taken here dotted structure I have represented. Okay, here NH3 will donate a pair of electron, so it is known as base, and boron trifluoride, it accepts a pair of electron, hence it is known as acid. Okay, next thing is ionizations of acids and bases. So it can be represented by Kw. Okay, what is you mean by ionic product of water? Here water is an weak electrolyte. It is a weak electrolyte. It undergoes partial ionization. And it can be represented by H2O is equal to H plus and OH minus. So it is a reversible reactions. Now let us apply law of mass action. H plus ion divided into OH minus ion divided by H2O means concentration of products divided by concentration of the reactants. Okay, so I'll take H2O on the left hand side. So you will get K into H2O is equal to concentration of H plus ion into OH minus ion. You will get. Next step, I'll take H2O, concentration of H2O will be equal to 1. So Kw I will get. Kw is equal to concentration of H plus ion into concentration of OH minus ion. So we can say the statements like this. It is the ionic product of water is that product of molar concentration of hydrogen ion and hydroxyl ion. Correct, right? It's a molar concentration of hydrogen ion and hydroxyl ion. Then it is considered as in aqueous solution, we have to say. It is in aqueous solution, not in a gaseous phase, only in a aqueous state. So we can say that it is a ionic product of water. Okay. Dissociation constant of weak acids. Now let us consider a weak acid HA which ionized partially in water molecule, and it can be represented by HA. It is when it is reacted with water molecule, and it will be a reversible reaction. We will get H3O plus, that is known as hydronium ion, and we will get a anion. And now let us apply a law of mass action. If we are applying a law of mass action, we know that K is equal to concentration of products divided by concentration of reactants. So I will apply a law of mass action to above equation. When we are applying a law of mass action to above equation, K is equal to concentration of hydrogen ion into concentration of anion divided by undissociated ions. Which and all undissociated ion? We have taken one reactant and it is dissolved in water molecule. So HA into water molecule. Now let us take a HA in downwards, as well as let us take water molecules on the left hand side. So K into concentration of water molecule is equal to concentration of hydrogen ion into concentration of anion divided by HA. So that we know that K into H2O, we can consider it as, that will be equal to 1. So concentration of water molecule I have taken 1. So Ka is equal to concentration of hydrogen ion into concentration of anion divided by concentration of undissociated ion. So at last we can define as it's a ratio of products of molar concentration of dissociated ions to the molar concentration of undissociated acid molecule, because here we have taken undissociated acid molecule because here just we have taken only a reactant. So I have said undissociated acid molecule to the given temperature. Okay. In next session, I will be studying about dissociation constant of weak bases or ionization constant. Thank you.